Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. So, we looked at the first order perturbation correction. As the first order. So, let me write En1 correction to the nth energy in the absence of perturbation to order lambda as the average value of the perturbing Hamiltonian in the eigenstates of the nth energy state, namely psi n0 H1 psi n0. Okay. And then we moved on to calculate the first order correction to the wave function, namely psi n1. And let me now bring the last screen that you had in the last lecture, so that we continue from that screen onwards. Okay. Now, if you recall this particular screen, to obtain the first order correction to the wave function, which is marked in green here by psi n1. Okay. What we did was to propose an expansion for the wave function psi n1 in terms of all the basis states of the perturbation free Hamiltonian, the eigenstates of the perturbation free Hamiltonian. But then we made a case by saying that except the eigenstate corresponding to that nth order, nth zero order Hamiltonian, that is psi n0, we will include all other terms. So, if you recall that the series for the first order correction to the wave function that you see here on this one, psi n1, was written in terms of a linear combination of all wave functions which are eigenfunctions of the perturbation free Hamiltonian with linear combination coefficients a and k, where k is such that it takes all the values other than the value corresponding to the nth eigenfunction. Okay. This was substituted in the equation for the psi n1, and then what we did was to multiply that equation by the psi m0 star and integrated both the left hand side and right hand side over all the coordinates to obtain this final equation. This is the one that I left you with in the last lecture, namely psi m0 star h1 psi n0 d tau plus sum over k not equal to n, a term containing the coefficients a and k, which we now have to calculate, and on the right hand side the corresponding terms. Okay. So, let us now complete this task of calculating the coefficients a and k. Okay. So, for that purpose, so let me do, we will start with a new screen. Okay. This is our current lecture. So, we wanted to calculate psi n1 and we had used this a and k, k not equal to n psi k0, and then we have this equation, namely the integral psi m0 star h1 psi n0 d tau plus the integral psi m0 H naught, and we had the summation over k not equal to n a n k psi k 0 d tau. Okay. This was the left hand side. Just let us check that that is what we have. Psi m 0 star h1 psi m 0 d tau plus sum over k naught equal to n a n k psi m 0 star h naught psi k 0. Yes, that is what we have. That is on the left hand side. Okay. Now, it is easy to look at this before we simplify this on the right hand side also. Let us do this right away here. Okay. We do know something about this integral, the second term. Okay, let me go to the full screen. And okay, we do know this particular term, namely this one. See that the operator h naught acts on psi k 0 on the right hand side or psi m 0 on the left hand side. It does not matter which we worry about, which one that we have to worry about, but this would give you the quantity psi m 0 sum over k not equal to n a n k. H naught acting on psi k 0 will give you e k 0 psi k 0, okay, d tau, okay, which if I put in only those which are needed inside the integral and leave everything else out, it is k not equal to n a n k e k 0 integral psi m 0 star psi k 0 d tau. Please note that when m was chosen in getting the wave function psi n 1, m was chosen to be not equal to n. Okay. If you again go back to yesterday's lecture, the previous lecture, the m was chosen such that this m is not equal to this n. Why? Because when we choose this m equal to n, we ended up with the first order correction to the energy already. Therefore, now we are looking at using the projections of this equation on all wave functions other than the wave function corresponding to this n. Therefore, if you go back to this, m is not equal to n. Therefore, it is possible that k and m can be equal, because k is also not equal to n. Therefore, there is at least one value of m, and there is only one value of m for which m and k are equal. Therefore, this summation will go away and this integral will turn out to be delta m k, and since here we are summing over k and this delta m k restricts the value of k to m, what you will get is a n m e m 0, where k is replaced by m. Only one term. All other terms in this integral will be 0 because the wave functions are orthogonal. Okay. So, the left hand side is simplified to now two sets, namely a term psi m 0 star h1 psi m 0 and an energy contribution a m, this particular term alone. Okay. So, the left hand side therefore becomes the following: integral psi m 0 star h1 psi n 0 d tau plus a n m e 0 m. What about the right hand side? Okay. Now, again if we look at the right hand side of the result that we had written down, there is again only one term, which is a n k, k not equal to n, e n 0 psi m 0 star psi k 0 star. Okay. Therefore, right away you can see this reducing to, because of this integral being delta m k, and therefore this summation in which k takes all possible values other than n, this summation is reduced to only one term, namely k is equal to m. So the answer would be a n m e n 0, and only for that this integral is 1, otherwise it is 0, okay, and there is no other term. So what you have on the right hand side is a n m e n 0, which we will now put in our equation here, namely right hand side is a n m e n 0. Okay. So out of all the coefficients, this way of projecting the operator or projecting the functions to the particular wave functions or the basis functions of the Hamiltonian gives you one coefficient. But we can now vary m. We can take the first wave function, the second wave function, third wave function, and therefore we can get all the coefficients a and m one step at a time. Now the summary is that the coefficient a n m, okay, times, if I bring this to the right hand side, the equation is that a n m e n 0 minus e m 0 is equal to the integral psi m 0, which we can now write using the Dirac notation. Okay. We will write using the Dirac notation, namely integral psi m 0 h1 psi n 0. Okay. So we have obtained the value for the coefficient, and of course the next step is to write explicitly a n m is equal to the integral psi m 0 h1 psi n 0 divided by e n 0 minus e m 0. Okay. So we have a coefficient, and therefore immediately the wave function psi n 1, please remember that the expression we used was k not equal to n a n k. We use the ket notation. We can start using now from this point onwards psi k 0, but we have the coefficient a n m. I mean the indices n and m. N is of course very specific. The running index is k, so the running index here is m, so it does not matter. I would rather write instead of k, suppose I write m here, m not equal to n. All I need to do is to make the corresponding changes here. The k is now in terms of m, and this is also in terms of m. So now we have an explicit form for this coefficient just in the previous line. So if you substitute that, what we get is the summation, namely m not equal to n psi m h1 psi n times the ket vector psi 0. Please remember this is a number, this is a complex number, and it's an energy, because the wave functions when integrated out will give you a number, and this is the Hamiltonian operator, the energy operator. So what you have is energy, and divided by this energy term E n 0 minus E m 0. So this is the wave function form for the first order correction, which we shall highlight, namely psi n1. The first order correction to the wave function is given by a sum of all matrix elements of the perturbing Hamiltonian H1 between that particular state n and all other states m which are not equal to n. This does not include the diagonal matrix element m equal to n. Please remember, its m is not equal to n. Therefore, we have no problem with the denominator. We have assumed that the energy states are non-degenerate. What does that mean? No two energies are equal, and therefore when the labels are different, the energies are different, therefore the denominator never goes to 0, therefore it is a well defined quantity for the first order correction to the wave function. This is what we need to use in order to obtain the second order corrections to the energy using the same method. Second order corrections. The second order here essentially means that terms associated with lambda square, where lambda is our perturbation parameter to the energy, and that is denoted by En2. Okay. Now, just to do that, okay, we have had about almost like 15-20 minutes. So let us take a short break here for about a few seconds, and let me write down the expression for En2 from the original equation that we are doing all these basic tricks, and then we will continue to derive the expression for second order, and hopefully in the remaining time also that just try and calculate one simple problem, that is, as an example, we will take either a particle in a one dimensional box or other problems where we do not have an exact solution and where we can use the perturbation theory. So we will pause for a few seconds break now. Okay. So second order correction to the energy, we need to go back to the equation H psi n is equal to En psi n and pull out the terms corresponding to lambda square, and please look back, look through your lectures a little bit back and then recall this term, namely H1 psi n 1 plus H naught psi n 0, sorry, psi n 2 is equal to E n 0 psi n 2 plus E n 1 psi n 1 plus E n 2 psi n 0. This is the coefficient of lambda square on the left hand side of this equation, the H psi n component, and the coefficient of lambda square on the right hand side is what you have here from E n psi n. So this was derived yesterday. Now what we need to do is do the same trick that we did, namely multiply this by psi n 0 star and integrate both the left hand side and the right hand side. This n is the same as the n for which we are looking for the corrections, okay, second order corrections. So when we do that, the equation is psi n 0 star H1 psi n 1 d tau plus the integral psi n 0 star H0 psi n 2 d tau, okay. And on the right hand side we do the same thing, namely psi n 0 star E n 0 psi n 2 d tau plus you have psi n 0 star E n 1 psi n 1 d tau plus integral psi n 0 star En2 psi n 0 d tau. Okay. So, you have on the left hand side 2 terms and on the right hand side 2 terms. We can look at this and cancel some of the terms immediately. Okay. Let us look at this term. You see that H naught acting on the wave function psi n2, which we still do not know what the second order correction to the wave function is, we only know the first order correction. Therefore, H naught can also act on the wave function on the left hand side. Being a Hermitian Hamiltonian, it gives you the eigenvalue corresponding to the psi n0 star, which is also En0. Therefore, this term is immediately, you can write it is En0 followed by this integral psi n0 star psi n2 d tau. Okay. No matter what the psi n2 is, whether this integral is 0 or not, we can right away cancel this term with the corresponding term that you have here, which is that, namely the psi n0 star En0 psi n2 d tau. So, they are both gone. This is gone, cancelled by that. Okay. So, what is left over is the integral psi n0 star h1 psi n1, and on the right hand side we have a couple of terms. Okay. We have En1, which is the first order correction, it is a constant. Therefore, this term can be written as En1 integral psi n0 star psi n1 d tau. Okay. Now, recall how we defined psi n1. We defined psi n1 in such that it does not contain the psi n0. It has all the linear combinations of all the terms, all the wave functions other than this term. Therefore, no matter what you do, how many terms you expand, this will be 0. Okay. Therefore, there is no correction. Okay. There is no correction from this term, it is all 0. So, what is left over on the right hand side is only one term. Now, we collect that. The right hand side is, of course, En2 is the constant that we are looking for. Therefore, if we write the right hand side first and say En2 times the integral psi n0 star psi n0 d tau, we know that this integral is equal to 1, and therefore, the right hand side has only one term, the second order correction that we are looking for. What does the left hand side contain? It contains again only one term, namely it contains this term psi n0 star h1 operator psi n1 d tau. Okay. Please note that the h1 does not act on the wave function to give you a diagonal correction, because h1 is something is a perturbation. Therefore, we do not have that property that h1 has diagonal, or it has both diagonal and off diagonal contributions. Therefore, the second order correction is given by this integral. But we know if you have to write this integral, it is in terms of Dirac-Ket, it is psi n0 h1 psi n1, okay, En2. Okay. Now, just by coincidence you might recall that En1 was given by psi n0 h1 psi n0, 1 and 0, 2 and 1. So, in principle, if I need to know the correction to any nth order or any kth order, whatever it is, third, fourth, fifth, etc., all I need to do is to do this quantity, calculate this quantity psi n0 h1 psi n k minus 1th order wave function, okay, if we have to calculate. Okay. Is it true or not? I want you to check it out, okay, in your calculation, but we will just now do the complete the second order correction, namely En2 is integral psi n, this is the ket that the bra state that we are writing, and now you remember psi n1 was given by an infinite, by a series, namely sum over, I think if I wrote probably m not equal to n, then we had psi m0 h1 psi n0 divided by E n0 minus E m0 times psi m0. Okay. This whole thing that you see, this whole thing is a complex number or real number depending on the value of this matrix element summed over. Therefore, you can immediately take that out and write this in a more compact form, namely sum over m not equal to n psi m0 h1 psi n0, and then we will write this part here, namely psi n0, sorry I should have a 0 here, psi n0 h1 psi m0 divided by E n0 minus E m0. Okay. Now, the summation is for both the denominator and the numerator. So, you have to be careful that you write this as m not equal to n. You have two wave function matrix, two Hamiltonian matrix elements, perturbation H1 matrix element, psi m0 H1 psi n0, psi n0 H1 psi m0, and if you know the Dirac-Ket the bracket properties, this bracket is the complex conjugate of this bracket. That is, whatever is the value of this, the complex conjugate, the starred value is what you will get here, and therefore even more compactly we can write this. A number multiplied by its complex conjugate is nothing but the absolute square of the complex conjugate. Therefore, we can write the sum as m not equal to n, the absolute value of this matrix element H1 psi n0 squared divided by E n0 minus E m0. Okay. This is equal to E n2, and this is a very, very standard second order perturbation theory correction for non-degenerate state. Second order correction to the energy of the system with non-degenerate state. So, what you are looking at is that you have a matrix element. If you recall the last lecture, I drew the matrix for H1 and I showed you that there are diagonal elements and off diagonal elements if you organize the basis functions of the zero order Hamiltonian in an order in the same order as you have it in the different rows and also in the different columns, then the matrix element between the bra state of a particular row, the Hamiltonian, and the Ket state of that particular column is what is called the matrix element of the Hamiltonian. So, now if you look at that, the term that you have here, namely the psi m0 H1 psi n0 is a matrix element, but please remember m is not equal to n, and therefore this is the off diagonal matrix element. Okay. The off diagonal matrix element, but unfortunately the perturbation correction does not depend only on that. The magnitude of the off diagonal matrix element squared divided by the energy difference between the corresponding diagonal and the off diagonal quantity. Now, let us see that pictorially what it means. Okay. Let us draw the matrix for H1. Okay. First, let us draw the matrix for H0. Okay. We know that the basis functions are eigenfunctions of H0. Therefore, the matrix of H0 is only diagonal. It is E10, everywhere else it is 0, E20, everywhere else it is 0. That is how we started the perturbation theory, that is we know a 0 order problem, the solutions to the 0 order problem, E0 and so on. What was the matrix for H1? We wrote the matrix element psi 1 0 H1 psi 1 0, and this first row, the second element was psi 1 0 H1 psi 2 0 and so on, as many basis functions. So if you have an infinite basis set, this matrix is an infinite dimensional matrix basis, the infinite dimensional matrix. And what is the second one? It is psi 2 0 H1, let me make sure that the hats are all there, and psi 1 0 psi 2 0 H1 psi 2 0, and of course this one is psi 2 0 H1 psi 3 0 and so on. Okay. Now, so if I have to write it even more symbolically, what I have is, I want to look at the correction to the nth element, that is the nth diagonal element. Please remember En 0, if it is here, En2 represents the second order correction to this value due to the perturbation. Okay. Now what you see is that the second order correction to this value is now given by a summation of all possible values with energy denominators. The energy denominators are, suppose you have En0 we start with, and let us put the first, here is the first one, the expression here. Let us assume that some value of n, m will be 1 to start with. So we take the matrix element of psi 1 0 H1 psi n0, whatever that n may be, divided by En0 E n0 minus E10. Okay. Therefore we are taking the if you write this as 1 2 3 4 corresponding to various matrix element 5 etc., sorry 1 1 1 2, I think that is a better way of writing it, 1 3 1 4 1 5 and so on. And if you do that, the perturbation correction to En2 is given by the matrix element, suppose this is 2, second energy level, then we have the matrix element 1 2 as the first item divided by the energy difference between 1 1 and 2 2. If n is 2, 2 minus 1, this 2 is the diagonal matrix element of the 0 order Hamiltonian, second row second column, so it is 2 2. This is the first row first column 1 1. So it involves the difference between the two energies and the corresponding off diagonal matrix element, this one. We are looking for correction to this term, okay, looking for corrections to this term En2, but it does not stop with that. It is also looking at the corrections to this is the next term in the summation. If you look at the m cannot be 2 but m can be 3. So 2 3 will be there here. When n is 2, m can be 1 3 4 5 etc. If m is 3, we have 3 2 divided by 2 minus 3. Okay. So 2 3 or 3 2, this is the 3 2 matrix element. Okay. So it involves a 3 2 matrix element, but the difference between the energies 3 and 2. And what about the next one? The next one will be 4 2. So if you look at the perturbation, what perturbation does is any energy gets corrected by the corresponding off diagonal matrix element with that energy and the difference between the two. Therefore, if you now assume that the energy levels are farther and farther and farther away, you will see that the matrix element is of the perturbing Hamiltonian has a certain value, but the energy denominators increase. If the energy denominators increase to very large values, but the matrix element of the Hamiltonian, perturbing Hamiltonian remains more or less the same, you can see that higher order correction, the corrections of terms farther away are going to be less and less. So all we can hope for is that if these energies are very far apart, that we even in that summation we don't need to calculate many terms. Okay. Let me just put that in perspective by writing an explicit second order correction to energy level 1. Okay. So we will do that. The expression would be n not equal to 1 psi m not equal to 1 psi m0 h1 psi 1 0 the absolute square divided by E 1 0 minus E m 0, isn't it? We had the correction is E n, yeah, 1 0. So if we expand to this, it's like this: psi 2 m will be the first value will be m equal to 2 psi 2 0 h1 psi 1 0 square by E 1 0 minus E 2 0 plus the next term will be m equal to 3, which means psi 3 0 h1 psi 1 0 divided by E 1 0 minus E 3 0 plus so on. So 2, 3, 4, 5, etc. If these denominators energies, if the energies are farther and farther apart as for the 0 order Hamiltonian 1, 2, 3, 4, etc., you can see that this itself, assuming that the magnitude of these matrix elements on the numerator are more or less the same, that they do not vary too much, assuming, you would see that these terms will decrease in size, and therefore as we compute even second order perturbation correction, we do not have to include many terms. It is possible that we do 2, 3, 4, maybe 5 terms of this, and then the corrections are not very significant, provided the energies E1 0 minus E m 0 is much larger, okay, than psi m 0 h1 psi 1 0 absolute square. Okay. Now this is a precise statement of the validity of perturbation theorem. That is, the difference between the 0 order energy levels connected by the perturbation, H1 connects 1 to m. Therefore, the 0 order energy level differences for those energies connected by the perturbations are very large. The magnitude of the perturbing Hamiltonian itself is very small, such that the ratio is much less than 1. That is a statement to say that perturbation theory will work very well when this condition is satisfied. Of the order of 10, when you take the ratio, that is E1 0 minus EM 0 is 10 times this, perturbation theory is good. 5 times the convergence is poor, and anything else it's poorer, and therefore maybe we'll have to calculate many more terms. Not only this, that's only for EN2, but if this condition is valid, if this condition is not valid, if this condition is violated, we may even need to calculate EN3, EN4, EN5 and so on. Therefore, we have to be very careful about the use of perturbation theory, particularly we need to check the magnitudes of the quantities involved, and this is a statement which you might want to remember as a condition for perturbation theory. Okay. So let me then summarize the results that we have for this lecture. We started with H naught psi n 0. Now everything is written in terms of the bracket notation as E n 0 psi n 0. Okay. The Hamiltonian that we used was H naught plus lambda H1, lambda to be set to 1 at the end of the calculation. So that the Hamiltonian becomes essentially, it goes to H naught plus H1. And now we have done the two calculations with lambda and lambda square. The first order correction E n 1 was given as the matrix element of psi n 0 H1 psi n 0. The first order correction to the wave function psi n 1 that we wrote was, just want to make sure that I don't have typos, sum over m not equal to n. We had psi m 0 H1 psi n 0 times the wave function psi m 0, the ket divided by the energies E n 0 minus E m 0, and finally the energy correction to second order E n 2 as the corrections psi n 0 H1 psi n 1, and that was given as sum over m not equal to n psi m 0 H1 psi n 0, the absolute square divided by E n 0 minus E m 0. Okay. These are the three most important results, and of course we have used the conditions psi m 0 psi n 0 is the Kronecker delta m n, which is 1 if m is equal to n or 0 if m is not equal to n. So this together is a summary of the two lectures that we have, and what we would do is in the remaining time that we have, we will start looking for one or two simple examples of how to apply these formulas. Okay. Now let us take the first problem that we want to look at as a simple example. We will consider the particle. I won't be able to complete that, but I will start this so that in the next lecture we will continue from where we left, and you will also have some time to look at and probably progress on your own to anticipate what I would like to say in that lecture. Okay. So let us take the particle in a one dimensional box. Okay. And we all know that the Hamiltonian 0th order is minus h bar square by 2m d square by dx square plus a v of x, where the v of x is such that v of x is infinite, very very large for say x less than or equal to 0, x greater than or equal to L, where L is the length of the box. Length of the box, and v of x is 0 if x is between 0 and L less than x is 0 less than x less than L. Okay. So the boundaries are at 0 and L, and at the boundaries and any point beyond the boundary on either side of the boundaries the potential is infinite, and inside the box the potential is 0. That is a correct form. Very often you use minus h bar square by 2m d square by dx square. Please remember that can lead to confusion, because remember that the wave function for the particle in the one dimensional box is not an eigenfunction of the momentum operator, precisely for this reason that the boundary condition has actually destroyed that the commutativity between the free momentum operator of the particle in a box and the total energy operator, which is not just p square by 2m, but it's p square by 2m plus v, such that v is infinite at all points other than the box and v is 0 at the points inside the box. These two statements have to go together. Okay. So if you remember that, then we will consider an artificial perturbation to the box problem. Okay, so sorry, that's a poor drawing. Let me just write. Let's see. Okay, this line is there because I can draw on top of it, but this line, let's just do that. Okay, so this is x is equal to 0, x is equal to L. The dots to tell the potential is infinity, infinity, and v is 0. Okay. Now we are going to consider obviously a perturbation that exists only in the box. There is no point in adding perturbations to the walls. It is already infinite potential. So let us consider v of x, the perturbation, or sorry, the h which we have been using, h1. h1 is a potential of this form c, some constant, times x into L minus x. Please remember, when we write the Hamiltonian, all the quantities that we have are operators. X is operator, x is operator. Well, L is actually a number, but L is multiplied by the identity operator, so I guess it's correct to put that L minus x. Okay. Now you see that the potential, the perturbing potential is 0 at the ends, but it's non-zero inside the box. And how do we calculate corrections to the particle in a box energy? What are the energies? The En zeros for the particle in the box are all given by h square by 8m L square n square, and the wave functions are all given by psi n 0 as square root of 2 by L sine n pi x by L. Okay, sorry, let me just write that carefully. Sine n pi x by L. Okay, so this is the 0 order wave function, and we also know that this integral psi n 0 star psi m 0. Here it's a coefficient. The degree of freedom is the particle position. Dx between 0 and L is delta nm. Now before I close, I would just like to tell you that this is the same thing as psi n 0 psi m 0, where you have seen that this x's and the integral dx have all been taken care of by this notation. Okay, that is, the integration over all the coordinates is not represented. I mean, it's understood when you do this bracket, and what you have is an abstract sort of a linear algebraic notation that the wave the eigenkets are orthogonal to each other, and the eigenkets in the coordinate representation are orthogonal as given by this integral. So we shall keep this in mind when we solve the problem of correcting the energies due to this perturbation in the next lecture. But if you wish to, please go ahead and solve some of these elementary things yourself before coming to the next lecture, before listening to the next lecture. Until then, thank you very much. Okay.